All right, picking up where we left off, the manager estimates that each customer who asks for a water cup but fills it with a soft drink costs the restaurant 25 cents. Suppose that in the month of June, 3,000 customers asked for that water cup when placing an order. Use the confidence interval constructed in A to give an interval estimate for the cost to the restaurant for the month of June from the customers who asked for a water cup but fill with a soft drink. So, from the previous video, we already saw that we're pretty confident that between 18.8 and 38.7% are actually stealing soda instead. So we'll start with 2. If it's as low as 18.8 or if it's as high as 38.7, because we don't really think it's going to be any lower or any higher than that. Multiply that by the 3,000 customers who get a water cup, and then multiply that by the 25 cents that they're losing. So on the low end, they estimate right about $141, and on the high end, they're estimating $290, $25. And that's another interval. So anywhere between, we're 95% confident that anywhere between $141 lost and $290.25 lost based on people stealing soda with water cups. Number 3, a grocery store purchases melons from 2 distributors, J and K. Distributor J provides melons from organic farms. Zoom in a little. The distribution of the diameters of the melons from distributor J is approximately normal with mean 133 millimeters and standard deviation of 5 millimeters. A, for a melon selected at random from distributor J, what is the probability that the melon will have a diameter greater than 137 millimeters? It already says it's normal, so we don't have to do any conditions. It says the mean is 133. Up here it tells us with standard deviation 5, so 138, 142, and 142, 147. Perfect. Nope. OC doesn't know how to count. 138, 143, and 148. Cool. Let's see here. Greater than 137. So 137 will be right about here. And it says or larger, greater than. Good. So something like normal CDF, on the low bound 137, high bound you got to go above the 3 standard deviations, so make it something really large like 999. That'd be a huge melon. 133 and 5. It should give you about 21.19%. Just some notation. Should probably say something like the probability that X is greater than 137 is equal to that. Distributor K provides melons from non-organic farms. The probability is 84.13% that a melon selected at random from distributor K will have a diameter greater than 137. For all the melons at the grocery store, 70% of the melons are provided by distributor J, and 30% are provided by distributor K. So let's label this. This was distributor J. This will be where I start writing about distributor K. So their melons tend to be much larger because it said 84% were larger than 137. So I don't exactly know where 137 lies on this, but we know something like 84.13% are larger as opposed to the 21.19 from the other one. We also know that this made up 30% of distributor J. I'm sorry, distributor J was 30%. No, I read that wrong. Distributor J was 70%, and distributor K was 30%. For a melon selected at random from the grocery store, what is the probability the melon will have a melon selected at random grocery store? What is the probability the melon will have a diameter greater than 137? So this is just kind of like a weighted mean or an so you'd weight that 70% coming from the 21.9 and 30% coming from the 84.13. So just weigh that out, and that should be about 40, a little over 40%. Let's read C. Given that a melon selected at random, so I'm already thinking of conditional probability. Given that a melon selected at random from the grocery store has that diameter greater than 137, what is the probability that the melon will be from J? So I'll write it something like the probability that it's from distributor J, given that it's greater than 137. So remember, conditional probability is a both over what was given. The probability that it's both from distributor J and greater than 137 we found on the previous one. So 70% of the 21.19% over, it says given that it's greater than 137, that's both of what we did earlier, a little over 40, and you should be able to calculate that right about 37%, little over. All right, this one is just reading box plots. The chemicals used in clay to make pottery can differ depending on the geographical region where the clay originated. Sometimes archaeologists use a chemical analysis of clay to help identify where a piece of pottery originated. Such an analysis measures the amount of a chemical in the clay as a percent of the total weight of the piece of pottery. The box plots below summarizes analysis done for 3 chemicals, X, Y, and Z, on the pieces of pottery that originated at any of the 3 sites, Site 1, Site 2, or Site 3. So Site 1 is first, Site 2 is in the middle, Site 3 with the stripes is the third. For chemical Z only, describe how the percents found in the pieces of pottery are similar, how they're different. Only look at Z. One similarity I see is that they look like they have a center or a median all around 7. The one thing that I see that's different is that the chemical Z in Site 2 was not very spread out at all, very consistent, whereas Sites 1 and 3 were far more spread out, with 3 being the most spread out. I'm going to abbreviate because I'm running out of room. The AP will actually give you room to write, which is nice. The spreads are different with Site 2 least spread and Site 3 most spread out. Consider a piece of pottery known to have originated at one of the 3 sites, but the actual site is not known. Suppose an analysis of the clay reveals that the sum of the percents of the 3 chemicals is 20.5. Based on the box plots, which site is it likely from? So look at it. Which one is, if it says, based on the block, a typical value, you want to look at like what the typical values would be. Like if you're looking at that first one, I'm thinking about 7, 14, and 13. So if I add all those up, it's going to be well above.